Call it the evolutionary march of the penguins. More than 50 million years ago, the lovable tuxedoed birds began leaving their avian relatives at the shoreline by waddling to the water's edge and taking a dive in the pursuit of seafood. Webbed feet, flipper-like wings and unique feathers all helped penguins adapt to their underwater excursions. But new research from the University of Nebraska-Lincoln has shown that the evolution of diving is also in their blood, which optimized its capture. Relative to land-dwelling birds, penguin blood is known to contain more hemoglobin, the protein that picks up oxygen from the lungs and transports it through the bloodstream before dropping it off at various tissues. That abundance could partly explain the underwater proficiency of, say, the emperor penguin, which dives deeper than any bird and has been documented holding it. Still, the particulars of their hemoglobin, and how much it actually evolved to help penguins become fish-gobbling torpedoes that spend up to half of their lives underwater, remained open questions. There just wasn't a lot of comparative work on blood oxygen transport as it relates to diving physiology in penguins and their non-diving relatives, said Signore, a postdoctoral researcher in Storr's lab. Answering those questions meant sketching in the genetic blueprints of two ancient hemoglobins. One belonged to the common ancestor of all penguin species, which began branching from that ancestor about 20 million years ago. The other, dating back roughly 60 million years, resided in the common ancestor of penguins and their closest non-diving relatives, albatrosses, shearwaters and other flying seabirds. The thinking was simple. Because one hemoglobin originated before the emergence of diving in the lineage, and the other after, any major differences between the two would implicate them as important. Actually, comparing the two was less simple. To start, the researchers literally resurrected both proteins by they found that the hemoglobin from the common ancestor of penguins captured oxygen more readily than did the version present in the blood of the older, non-diving ancestor. Unfortunately, the very strength of that affinity can present difficulties when hemoglobin arrives at tissues starved for the oxygen it's carrying. But then you're at a loss when it's time to let go. Any breath-holding benefits gained by picking up extra oxygen, in other words, can be undone if the hemoglobin struggles to relax its iron-clad grip and release its prized cargo. The probability that it will is dictated in part by acidity and carbon dioxide in the blood. Higher levels of either make hemoglobins more likely to loosen up. They also illustrate the value of resurrecting proteins that last existed 20, or 40, or even 60 million years ago. Please support our channel to grow by pressing subscribe button as well as the bell icon for daily updates. Thank you.